Last time we started section 1.2, we had talked about at the very end these things called delta epsilon proofs, or epsilon-delta proofs. And we had talked about how we go about finding what delta is based on setting up this inequality with epsilon in it. Okay? So we had this precise definition of limit, and we're going to use much of what this precise definition is and what it says to actually do our proofs. Yes?
Do we have to memorize this definition for the quiz, or is that not until the
No,
test?
not till the test. Yeah, just for the test. So it's still a couple of weeks away. Yes, good question.
Still Numerical.
Yes, you probably shouldn't wait until the night before the test, because as much as I would like this not to be true, there's going to be probably 3 or 4 people in here who are not going to memorize this, and I wish that weren't true. But just statistically, from my past experiences, that's probably going to happen. And don't let it be you. That's all I can tell you. So, yeah, prove the statistic wrong. Okay, let's take a look at problem number 4. Okay, the first thing problem number 4 says is to find the limit. And then the next thing it said is to use the delta or epsilon delta proof, definition, to prove that the limit is that value L. So we're going to find it using numerical methods for one of these problems, and we'll do it using a graph for the other one. Sound good? Okay, so let's do the numerical on the first one. And whichever one you do, you're going to have to show work for how you found the limit for this section. We're going to have another way to do the limit when we get to 1.3, and that work looks quite different. Okay, so in 1.2, make sure you're showing one of these 2 methods, because up to this point, this is all you know. Okay? Y'all with me? Okay, fantastic. Okay, so we're going to do a table. If you'll remember the way that these work, we put the 2 tables here. One of them have x values that are smaller than the x value that we have, and the other one larger. So this x value on this one is -2, or we're approaching -2. All right, so we need -2 from the left. What are values that are slightly smaller than -2?
1.9.
That's slightly larger.
Negative 1.9.
Okay, -1.9 is actually slightly larger.
Oh, yeah.
Yeah, because we've got the negatives going on, right?
Yep.
Yeah. Okay, so these are the 3 that we would have for that side. What would be the ones that are slightly smaller?
Negative 2.1.
Mm-hmm. All right, and we'll find the f of x values. All right, so we're going to put this into our calculator.
But I thought this was the numerical one.
The what?
Okay, so
This is the numerical one. We have 2 ways right now of finding limits, numerically and graphically. So what we're going to do after this is going to prove that this is the limit using the delta epsilon proof. But we have to find the limit in order to use the delta epsilon proof first, okay? We have to know what it is. All right, so in your y equals, you're going to put in this equation, 3x plus 2. And you're going to go into your table. And all my values are not what I want. Let's try this.
Oh, yeah.
Oh, yeah, that's not going to work.
Too bright.
It's really dark, but the other one's way too light. All right, well, we're just going to have to go with it, I guess.
You could change the setting on your calculator.
That's true, I could do that. That's not going to do it. I'm just not having any luck. I'm wondering if it's darker in here today. It feels like maybe it is than it normally is. I don't know. All right, I've got values anyway, and that's what I was wanting over here, right? So if you are looking at yours, oh man, that's too full. We're just going to go with it, okay? All right, let's fill these in. We've got -4.3, -4.03, and -4.003. And then on the other side, we have -3.7, -3.97, and negative 3.997. And so using these pieces of information, we believe that we have the limit as x approaches negative 2 of our function, which we'll call it f of x so that I don't have to rewrite it all out, okay? We believe it's what? Negative 4. We believe it's negative 4. That's what it looks like, right?
Yep.
Okay, next we're going to do, so this is something we've already done. The next thing we're going to do is we're going to take a look at the epsilon-delta proof part that we did last time and what that would look like. So we're going to set up an inequality. Inside of the inequality, what do I write first? Yes.
Well, I actually had a question.
Yes.
about this.
Okay.
Is there like a specific reason that we don't just put the value that we're looking for?
We're going to get to that point where we can do that. The problem is that sometimes, depending on the equation you have, if you actually put the value in, you get something that doesn't exist and it doesn't give you a value at all. And what we don't want you to think is that simply because there's not a function value there, there's not a limit there. Because sometimes if there's not a function value, there's still a limit. So a limit by definition really just means you're getting really close to the x value. You don't actually have to equal the x value. Now, if the graph is what we call continuous, which we'll get to in section 1.4, then it's the same thing, and it doesn't make any real difference. So that's not really a direct answer to your question, I guess, but there are possible complications.
So like we're looking forward
Right.
to things that we're going to have.
Yeah, exactly. Yep. Yeah. All right, so inside of our absolute values, what's the first thing we write with our delta epsilon proofs? Yeah, the function that we're given, the equation we're given. So, and it's the 3x plus 2. Right? Do you remember what you put next? Minus the value it's approaching, and that's the value we just found. So this one will be minus a negative 4. Be careful that you're getting both those negatives in there. If you have only one of them, it's going to make the answer wrong in a minute, and things will all fall apart, and you'll be like, what happened? Okay? And then what goes on the other side? That's where the epsilon goes. Okay? Now, our goal in simplifying this is to get it to look like x approaching this number. So what is our goal here going to look like? It's another absolute value. What is it going to be the absolute value of? We'll start out with x. And then what?
Plus 2.
Yeah, it'd be minus the negative 2 or plus 2. Okay? It's always x minus the x value that we're approaching. Okay, so our goal is to change the expression right here into something that says x plus 2 is less than something. That's what we're looking for. Okay? So as we simplify, we end up with 3x plus 2 plus 4 it's less than epsilon. So 3x plus 6, obviously. Okay, what did we do next?
Factor out a negative 3.
Yeah, ours is actually a positive 3. We're going to factor out a 3 because they're both positives, right? 3 and 6 are
I was
positives.
just thinking to get it to negative 2.
We aren't going to get it to negative 2. We want it to be positive 2.
Oh, that's right.
Yeah, because we have the two negatives here. Yeah. Yeah, so we're going to factor out a 3. And we can factor it out straight away just as positive 3 because the absolute value of 3 is 3. So in taking it out of the absolute value, it doesn't even change signs on this one. And then we can divide the 3 to the other side. Okay, so that kind of brings us up to what we've done so far. We've combined two pieces of what we've done into the same problem, but we have one more step to go that I haven't shown you yet. Okay, it's the writing of the proof. So how many of you took geometry where you wrote proofs at some point in your distant past? Okay, so a lot of times when you do geometry proofs, they're two-column proofs. You sort of put, you know, the steps over here and then the reason for it over here, right? Another way of doing proofs, and you may have seen them, are called paragraph proofs, where you're kind of justifying as you're going along, and it looks more like a paragraph of writing, okay? Well, that's what we're going to do. It's going to look more like a paragraph of writing, but it's going to have some mathematical notation inside of it, but it's going to look like a paragraph, okay? So our paragraph is going to very, very, very much feel like this definition. And here we go. So we're going to write something to the effect of this.
Does the epsilon over 3 equal delta?
It does.
Okay.
I'll write that in, thank you. Yeah, this is the delta that we were looking for, right. All right, we know that the limit as x approaches -2 of 3x plus 2 equals -4. I mean, that's what we were trying to say anyway all the way along, right? That is the limit. We know this because for every epsilon greater than 0, there exists delta, in this case, equal to epsilon over 3. Okay, so this is the part where it actually affects with the that value of delta you found, such that when, and then this is where it looks like we're going backwards of how we actually worked through the problem. When x plus 2 is less than that delta, then f of x, that's our 3x plus 2 minus the -4, or you can put plus 4 if you'd like, is less than epsilon.
I have a question.
That's the proof. Yeah.
So we're not gonna do any like finding delta thing, like d1, delta 1, delta 2. You pick one of those. Like.
We're going to do something about that in the next problem that might be closer to what you're talking about.
Okay.
We are going to have to make a choice on something in the next problem anyway. Yeah.
Been a while.
When it's a linear equation, we don't have to. Linear equations are really clean. They're very straightforward. So what is this saying? This is saying that the limit really is -4. And the reason that the limit really is -4 is because if your x value is really, really close to -2, right, that's that x plus 2 part at the bottom. If it's really, really close on the x value to -2, you're going to be really, really close to the y value of -4. That's what that definition meant for us to do. And this is what the theorem, what our proof actually says happened. Okay? So this is the proof that that value actually is our limit value. All right, we're going to do one more. I promised you that we could do this one graphically. So take your calculator, and we're going to put this into the calculator, but we're going to look at the graph for it. And the x value we're looking around is the x value of 2. So if you would like, you could actually just look at the top quadrant, not the top quadrant, but the right-hand side. So go ahead and graph x squared minus 3, which looks an awful lot like what?
Linear.
Yeah, a parabola, right?
It's a lot like the parent function.
Yeah, a lot like the parent function x squared. And then what's the minus 3 going to do to our graph?
Put it down.
Yeah, it's going to move it down 3. So this is what it looks like. We really only care about the right-hand side. Honestly, we really only care about the values near x equal to 2. So I'm going to make my window just, in fact, I think I'm just going to zoom in a little bit. Let me try that one. I want to zoom in over here where I'm getting close to an x value 2. So if I trace over here close to like x equal to 2, then that's kind of where I'm going to zoom in at. That's going to be the center of my zooming in. So my screen looks something like this. And all we're going to do is we're going to hit the trace button. We didn't have to zoom in, by the way, but we're going to hit the trace button, and we're just going to trace along our curve until we get close to x values of 2. And we're going to estimate, basing on that, what we think the y value is really close to from the graph. Okay? Near x equal 2, what is the y value that we're close to? So the graph looked something like this, I think. Right? This is my screen. The zoomed in part, okay, just like that on the board. What does it look like from a graphical standpoint that the limit is? Looks like it's at about 1, right? All right, so if you're not told that you have to do it graphically or numerically, you can pick whichever one you'd like. It doesn't matter to me. But if you're going to choose, well, whichever one you're going to choose, you're going to have to justify it with work. So what does the work look like graphically? Well, it looks like actually creating the graph on your paper, if you're turning it in like that, right? Or creating those tables. So you're going to draw one or the other. All right, so let's go through the delta epsilon part of this, because this one will look different because it is a quadratic, all right? It starts out the same, though. We're going to start out with the x squared minus 3, the function value, and we're going to subtract the value that we just got as what we believe our limit value is, which was 1. Okay, so now I have x squared minus 4. So unlike the linear one, I don't have just a constant that I can pull out, right? But any ideas about what you could get that x squared minus 4 to do that might be nice? Yeah, and we call that factoring, right? We could factor that. Now, before I do, let's go back up and look at what our goal was up here. This right here tells me what our goal is at the end. Our goal at the end is to get x minus that x value that we're approaching, so in this case, x minus 2. That's what I'm looking for. Now, if I factor what's on this side, I have x minus 2 and x plus 2, like you guys mentioned. So is one of those pieces what I want? Sure is. One of those pieces is, in fact, what I want. All right, so the one that I want, I'm not going to manipulate with. Make sense? Now, it is reasonable and allowed for me to change this so that each of these individually is inside of an absolute value instead of both of them multiplied. Because obviously if both of them are positive, then the whole result multiplying them is going to be positive, right? Pretty good with that? Okay, and the one that I want to keep is the first one, yeah? It's the second one that I need to turn into something else. I can't just divide it to the other side. And the reason I can't is because it still has a variable in it. I need to divide something to the other side that's just a number. Okay, so there's a trick to doing that, and that's why I'm showing you this, so that you can see what this trick actually looks like. What we want is we want the x value to be very close to the x value of what? 2. We want an x value that's close to x equal to 2. So we're going to say that we are going to let our x value be between 1 and 3. Because if you're between 1 and 3, are you pretty close to 2?
Yes.
Yes. Is there anything special about 1 and 3? No, it's just what I picked. All right? If you wanted to pick 1.5 and 2.5, have fun. Pick 1.5 and 2.5. Okay? I picked 1 and 3 because they're integers. They're nicer numbers to work with. They're 1 unit away. They're still fairly close to the x value too. Okay? Nothing special or magical about it. So we're going to let that be our x value. So using that, what I want here is I want to plug in the x value that's the largest. That's not hard. Which one is it? 3. So I'm going to plug in the largest x value. So I want to leave this x minus 2. Don't move that one around. We can't plug x there in as 2. That's not a good idea. But over here, I can. Because my whole goal is to get that expression right here to be as big as possible. I'll show you why in a sec. But our goal is for that to be as big as possible. And 5, which is what we're going to get when we plug in 3, is going to be bigger than 3, which is what we get if we plugged in 1. Okay? So we just want that to be as large a possible number. Okay, so now I have x minus 2. I have 5. And we can divide by the 5, okay? Okay, so is everybody good with where this ended up at this point? Now let me talk about why I chose this result to give me 5 and the result instead of the result to give me 3. This is the delta. If I divide by 3 or if I divide by 5, which one gives me a smaller number? 5. Divide by a bigger number, you get a smaller number, right? 1/5 is smaller than 1/3. Well, if I have 1/5, or in this case epsilon over 5, instead of getting an interval that looks like this, I get one that's smaller, right?
Yeah.
So the bigger value I divided by gives me a smaller interval, which means it's closer to the value I wanted. That's the goal, right? It's a limit. I want to be as close as I can.
But why in that case then didn't you just pick like 1 to 4?
Because I'm not as close as I was before.
So you want it to be close, but you still want it to be big.
I want it to be close. I want the x values that I'm picking to be a close x value, but I want the maximum that I would get from the interval I choose.
Okay.
Yeah.
So you could literally choose like 2.1.
You could. I mean, you could go from 1.9 to 2.1. That's fine. And then in the end, you'd end up dividing by 2.1 plus the interval. I mean, that's okay.
Yeah.
You can.
And-
Your book tends to use this kind of a pattern where they go one in either direction and then choose the larger one.
Would it not change your answer if you used a different interval?
It will change the value you're getting for epsilon,
Okay.
right? So it will change the delta at the end, right? The epsilon over whatever you get, so it'll change the value for delta, but it won't change the proof itself because it'll still be proving the same thing. Yeah. All right, now, hopefully you're getting a feel for why this part is not in WebAssign, right? You can't write this paragraph in WebAssign because you've got some arbitrariness in how you're picking your interval and so forth. How would WebAssign know what to grade correct and incorrect? So that kind of answers part of why we're using WebAssign as well. We need to write out this proof. Sorry, I've got this bright white screen now, but we're going to go with it anyway. So it starts out much the same way we did before. We know that the limit as x approaches 2 of x squared minus 3 equals 1 because for every epsilon greater than 0, there exists delta equal to what? Epsilon over 5 by the work we did. Such that when the absolute value of x minus 2 is less than delta, or you could write epsilon over 5 there, that would be a 5. It's less than epsilon over 5, then the absolute value of x squared minus 3 minus 1 is less than epsilon. Okay?
Are they all gonna look like that?
They're all going to look like that, yes. So there's two things you're going to essentially have to memorize. You're going to have to memorize the actual definition over here that we did for piecewise limit, or for a precise definition of limit. But do you see how much of that language looks just like what we wrote down?
Yeah.
Yeah, I mean, like that last part right here, especially all of this,
Yeah.
is almost exactly what we wrote down. There's very little difference between what we have written down in those last two problems and that statement right there. Okay? And when you do get to your test, I will ask you to do one of these on there. Okay? I'm not going to ask you to do one on the quiz on Wednesday. The reason I'm not is because you're going to be turning in homework that's going to have several of them on there for me already. Okay? So the quiz is going to be focused on the other components that have been more the WebAssign stuff that you've done.
So
Yes,
all
ma'am.
the questions out of the book, we will be writing that paragraph.
I believe that is correct. Yes.
There's only 5.
Yeah, okay. I thought there were going to be 6, but 5 sounds awfully close. So I was remembering close to the right number. Yes. Yes, ma'am.
Can we do one where there's like one of our homework problems, it's like x squared plus 4x, there's 2 x's?
Okay, it doesn't change anything. It just changes how it factors. So instead of factoring as like this was a difference of squares, the factoring will be using, properties of factoring from algebra. Okay?
So like you could take out an x.
So it might be like x plus 2 and x plus 7. Like your factors won't be matching. They won't be x plus 2, x minus 2. Yeah, and your book, I'm sure your book has some examples of some factoring things, but if it's a factoring issue, that's something the Success Center is going to be fine with helping you with too. It's just a factoring problem. So, yeah. Yes, sir.
Work-wise, how are you like showing every step?
Just like what I did on the screen here. This is what I would expect to see. You might not have every single detailed step out, right? Like you might not actually need to write out that the minus or the plus 2 minus a negative 4 ends up being plus 4, so. But you need to show one of these 2 steps at the beginning. I mean, it's going to show one of those 2, so probably the first one in general. And then you might jump to here, right? And then legitimately, you might jump down to here, depending on how, how secure you are in your algebra skills. Okay, so show what you need to show, but make sure you don't skip something along the way. And the kicker is, if you do not get the x plus 2 that I'm getting here, because we said that's our goal, you've made a mistake. So if at this point you get x plus 4, go back and figure out what it is. You might have missed a sign. That's usually what people miss, is they miss a sign along the way somewhere. So be aware of the fact that that should happen every single time, or you've got a mistake on your work.
So is it just always like x